So today we have a special astrophysics or physics colloquium, rather interdisciplinary, as you will see, like at the border between astrophysics of binary black holes and plasma physics, and experimental plasma physics. And so our speaker guest is Ali Kurmus, who has just finished his undergraduate studies at Harvard University, Department of Physics. And during his studies, he has been very active. So you did several internships. So for example, you worked or did your internship at CERN, at Atlas experiment. Yeah. Then you also did some studies of Vera Rubin telescope, like the effect of dome seeing, also some cosmological studies using James Webb Space Telescope, and then finally also you did this kind of study that we have recently collaborated on, so on binary black hole systems as gravitational analogs to ion traps. So it seems that you did more than like an average postdoc during your undergraduate studies.
No.
But in any case, you will soon start your PhD studies, PhD research at the University of Washington in Seattle.
Yes.
So please give us some answer what an ion trap is doing out there in binary black hole systems, please.
Of course. Okay. For everyone, welcome to my talk. Can everybody hear me in the back of the room as well, or do I have to speak a little louder? Okay, that's wonderful. Well, I also would like to give a small introduction to myself. Mikhail did a great job, but I'm Ali Kurmus, and actually this project came up on an unofficial talk in an office hour when I was teaching quantum mechanics with Louis Delurier. We were talking about quantum computers and ion traps, and we said, oh, maybe it is similar to some binary systems in the astronomical settings. And we said, oh, binary black hole system, charged black holes. Then we realized, as physicists, we don't know much about black hole and black hole charges. And that's how we reached out to Mikhail all the way in Czech Republic and started this collaboration. This talk is titled, what is an ion trap doing out there? And yeah, it's a great question. And more officially, binary black hole systems as gravitational analogs to ion traps. I'm aware that this sounds a little too complicated because there are ion traps, black holes, how do they all come from? So well, let's start with what are ion traps. As you could have guessed, it's a setup used to confine charged particles in a certain spatial region. And they are used for quantum computing, atomic clocks, plasma physics, and many other uses. There are many kinds of ion traps, but one of the main ones that we are going to argue that are analogous to binary black hole systems are Paul traps and Penning traps. So before I start talking about ion traps and black holes and show you guys equations and get excited, let me tell you why is this analogy interesting. Well, first, because it is interesting. I want you guys to pause for a moment and think about it. An ion trap is something that is very small, made in a lab to capture something very, very small, a single atom. And binary black hole systems, or binary systems in general, are huge. They're in the outer space and they occur fully naturally. And these kind of very disparate entities being related to each other somehow is quite interesting, and it opens up a lot of possibilities as well. And the second thing is that actually non-orbital gravitational trapping has not been studied before. When we think about confining a particle in a certain region of space by gravity, we always think about orbits. Yes, a particle or a thing orbits another body. Yes, it is staying there, but it's not really confined in a certain spatial region. Well, you may talk about Lagrangian points because we have seen it in astrophysical astronomy classes, and you probably would think L4 and L5 are possible examples of trapping gravitationally. But both L4 and L5 have a very, very tiny trap depth, so if a particle just comes in with a speed, it immediately escapes. Also, they only confine particles in a two-dimensional region. The third dimension, the particle is free to move. What we are going to argue is actually trapping in 3 dimensions using gravitational. And finally, we will claim that they're analogous setups, but it wouldn't have mattered too much if we just can't see them, if they just existed somewhere. But what we are going to argue is that with the setups we can have an electromagnetic signature from it and prove its existence observationally. So before further ado, let me start talking about the first comparison, the Paul trap. The Paul traps are setups to confine charged particles, and you can see that, let me use this, there are two end caps kept in a static potential, and they confine the particles in the z direction. As the particle tries to escape in this direction, it is pushed inwards. And then there's a ring that is confining the particle in the x and y plane. And the ring constantly changes the electric field. So as the particle is trying to escape to one direction, the electric field is changed and it's pushed toward the other direction. And I will talk more about this setup. I just want you guys to visualize what a Paul trap looks like. And the second setup was a Penning trap. Again, we can see the end caps similar to Paul traps. And end caps, again, push the particles within the z direction and confine them. And they are kept in a constant potential difference with the ground. And then the inside in the xy plane, the particle is trapped by a magnetic field. So the particle is doing a cyclotron circular motion. And Paul traps are actually quite revolutionary. They are not a simple lab setup that some sort of plasma physicist or ion physicist use. They are solving one of the most fundamental problems of electrostatics. Maybe you have seen this problem in introductory electrodynamics, but a charged particle cannot be in a stable equilibrium just by electrostatic forces alone. So Wolfgang Paul just solved this by changing the electric fields and creating some sort of a dynamic stability. Well, how does this dynamic stability work? I think this illustration tells it pretty well. We have two things on the side represent the rings that are trapping in the x and y direction. And in the first picture, the particle is pushed inwards in y direction and outwards in x direction. And as it is almost going to escape, whoop, electric field changes, and suddenly now it's pushed in the x direction and outward in the y direction. And this kind of a dynamic stability will be like, oh, how does it really work? It's kind of fishy, you know. Is it too good to be true? But it's not. Paul traps are quite stable. In fact, you can trap a single particle for weeks in these setups. And the reason I said weeks is that I think there was no experiment that trapped it for months or something. So maybe you can trap it for months. And although there's a dynamic stability, it's one of the cleanest of the quantum systems to analyze. And that's why it's the leading method for quantum computers. And here is a picture of an ion trap, like the Paul trap, and you can see the relative scale of it. You can see the end caps, you can see the rings. But this talk is not, unfortunately, just about Paul traps. I have a lot to go through. So if you want to learn more about Paul traps, you can always use ChatGPT. It will probably give me a better summary give you guys a better summary than I did. Well, I just talked about dynamic stability, but usually, even if I completed my undergraduate, electrodynamic examples are not really intuitive for me, and I like to think about mechanical analogies of some sort of a dynamic stability. And rotating saddles are actually a great example of an analog sister system for this, because a saddle potential is not really stable by itself. As you can see, if the particle moves anywhere, whoop, it will escape. But if we rotate the saddle in a certain frequency, we can create a potential well that ends up making the particle in a stable trajectory. And the concept of dynamic stability is that a system that is not stable by itself being stable after introducing some sort of a change. And I agree that this rotating saddle is different than changing electric fields because this is rotating and the electric fields are constantly changing. That is more of a flapping potential. But we can still consider this as we would like to put a sister system. And unfortunately, I lied to you guys, and this is just not a mechanical analog. This will be the basis of our comparison with Paul traps and binary systems. How would that be possible? Well, a gravitational binary system reduces to an exactly rotating saddle near the center when we do a Taylor expansion. I said a lot of concepts, so let's back up a little bit. There are ion traps called Paul traps, and then they use dynamic stability to confine particles in a certain spatial region. Rotating saddles also use dynamic stability to confine particles in a certain region. And binary systems, gravitational binary systems, reduce to a rotating saddle in the center of the system. And we're going to continue our analysis further in the rotating saddle approximation. Well, let's actually talk about our binary system and how we claim that we trap sort of a charged particle. In our system, we have two black holes that are rotating in the plane of rotation, and they have a mass, they have an electrostatic charge, and one of them is located at negative B, one of them is located at B, and the gray region that we see here is the region that we claim that the potential exactly reduces to a rotating saddle. The square roots and all the nonlinearities in the Taylor expansion are too small in this scale, and we can trap a charged particle in this region. So far, so good? Okay, well, this is quite simple of a system, right? There are a lot of binaries, but we have never talked about something being trapped in the middle. Why didn't people think about that first? Well, to understand that, we unfortunately have to go to school a little bit. So I'm going to flash you with some equations in the next few slides. I'm going to explain what all these equations are about, but please do not worry if you do not immediately understand when you see them in the slides. But if you do, you're just smarter than I am. So let's talk about the dynamics of the ideal analogy that I showed. We claim that the system reduces to a rotating saddle, and you are familiar with this hyperbolic potential, and this constant on top just adjusts for the gravitational and electromagnetic attraction. And you probably saw the primes on the x and y. That just incorporates the rotation of the saddle by a change of variables. And there's a difference between a rotating saddle. The omega that we define in this equation is actually not an arbitrary thing. It is defined by Kepler's gravitational laws. So we have to have this fixed omega. And also, let's introduce the symbol k to make the notation simpler for the next slides. That is just describing the constant of pushing and how the saddle is reacting. Now, these are the resulting equations of motions when we use these dynamics. Of course, on the x and y plane, this is like incomprehensible. There are some complicated stuff. I see some cosines. I don't know, there's a second derivative. Too complicated for now, so we'll talk about that later. But on the z direction, this is a harmonic oscillator. You probably immediately have noticed that, which is nice. We were going to argue that there were 3 dimensions of trapping, and we already got 1. Okay, the next 2 is unfortunately a little more complicated. To make this an exact expression like a rotating saddle, we use this change of variables. So we introduce a dimensionless time and 2 parameters A and Q, which makes the equations of motion in 2 dimensions more manageable. But still, what are these A and Q? They're actually just not random variables that make the equations look better, but they are the stability parameters in a rotating saddle. And I also want to note an additional similarity. Even though in a rotating saddle literature, this alpha can be anything, when in our gravitational binary setup, this alpha has to be exactly equal to 2 because of the way the system is set up. That restricts that A and Q follow this relation of A equals to -2/3Q. So now I said A and Q are the stability parameters that are for particles that are governed by these differential equations, but how would that be possible? And this is the plane of stability. A represents the asymmetry of the saddle, and Q represents the steepness of the saddle. And a combination of these A and Q will give us a plane of stability and regions of stability in an AQ plane. And if we have a purely gravitational potential without black holes having a charge, then this ends up being too steep and takes us to values of Q that are approximately 4 and way, way, way further than our current stability diagram describes. And then what is the physically possible stability region? because I just said something's unstable, and I just said that we have a system, and now I'm saying it's unstable. Well, introducing an electric charge to black holes makes the system analytically stable. You can see the small square right in there describing the stability region, and you can see the relation A is equal to -2/3Q, and this part describes how adding a black hole charge carries us within the stability region. And here, if we go make the charge a little smaller or no charge, as you can see, we go way, way, way beyond the stability region. These specific values of A and Q and the stability planes are quite complicated in the sense that it's not really possible to describe it in 2 minutes of a 40-minute talk. But what physical values correspond to these things can be explained better. So for a proton that is trapped between two 1 solar mass black holes that are 2 AU apart or have an orbital radius of 1 astronomical unit, and a black hole charge of 133.2 coulombs per solar mass, results in a stable trajectory of A being equal to -0.47 and Q equal to 7.705. What do these things mean, or what do these slides mean, is that we analytically proved the existence of a stable trajectory. That is all you have to take from the couple of previous slides, but I could not just have shown you this and said this is analytically stable, but this is quite exciting because we have shown that by gravity, analytically, we can trap some particles within the black holes. However, this was an ideal analogy, and life is not ideal. There is a background field in the background magnetic field in the universe, and that introduces a velocity-dependent term to the beautiful equations of motions that we have. Also, yes, the magnetic field is bad, but most of the systems that make black holes have a charge, that let black holes have a charge, involve a magnetic field. So we cannot just neglect background magnetic fields. Also, we said this all works in an approximation, a Taylor expansion, but of course the Taylor expansion is valid until a certain limit of spatial region. That's why we did not account for the nonlinearities in the black hole or this system has. Because there are nonlinearities, combination of this magnetic field and the nonlinearities makes this system analytically unsolvable. But still, as you probably all have been used, we can do numerical simulations to solve these things. So what do the numerical simulations tell us? Well, this is the resulting trajectory of a particle of a proton that are trapped between two solar masses, yes, 1 solar mass black holes, 2 AU apart, with a magnetic field of 10 to the -13 Gauss, starting from 10% of an AU on the X direction and 10% of an AU in Z direction. This trajectory or this plot may not make sense too much, but the only thing that you have to take away from it is that the starting point is in the sphere of it, and the ending point is also within the sphere, which means the particle has had a stable trajectory and only was around a radius of 10% of the orbital radius. But we have now shown analytical possibility of stability, and also we have shown that even with perturbations to the ideal model, this thing is stable. But how plausible is this system? Because I set very specific values. Well, the mass of the black holes are accurate with the literature, for stellar mass black holes, and they do have small enough accretion disks so that we can neglect the accretion disk in the simulations. And the charge that we claim the black hole should have are also consistent with the literature. And the background magnetic field also agrees with the literature. But I, of course, told you guys the good news first. Unfortunately, there are some bad news. The black holes in our systems were equal mass. And in an astronomy notation, in the papers we have read, this is denoted by the parameter mu, which is the ratio of one black hole to the total mass of the two black holes. And equal mass ends up being 0.5. Mu equals to 0.5. Unfortunately, tolerance of this trap is only up to mu equals 0.505, which means the black holes have to be within 1% of each other's mass. well, this obviously decreases the likelihood of such a system, so this is bad. On the other hand, detected merger systems of stellar mass black holes actually claim that most of the black holes in the binaries have a mass distribution near unity, which is nice. This maybe says that our system is not that unlikely at all. So what did I tell all of these things for? First of all, with a black hole that possesses a stable charge, phenomenologically, we can make an analog of a purely artificial setup with a purely natural setup. That is by itself wonderful. It's a small toy paper, maybe it's a grad student exam question, but it is still useful. And we also showed that, which has not studied before, a non-orbitational gravitational trapping is just, again, phenomenologically possible by charged binary black hole systems. And these things opens up possibilities of further research, of just looking for artificial analogs in the universe. And I had not seen literature regarding that before, so this is also exciting for me. And finally, I do have to acknowledge that most of the results are only phenomenological, and I have repeated that word many times, because maximum of 1 mole or 1 gram of particles could be trapped in this setup. Why is that? Because we can only trap like charges in the system, and like charges repel. However, we have another setup that I actually hinted in the beginning of the presentation, which are penning traps, and can trap much larger mass, much more versatile, and much more exciting to look at. So how can we make an analogy with a penning trap and a binary black hole system again? Let's recall what a penning trap was. Again, penning trap, the end caps of the trap have an electrostatic thing. We force the particle be trapped in the z direction, and the magnetic field traps in the x and y direction. So if we make an analogy with a magnetic field or with a binary black hole system, call it gravitomagnetic penning trap, we have, again, 2 black holes orbiting each other, and we have a magnetic field that is aligned perpendicular to plane of rotation of the black holes. And the magnetic field, again, confines the particles in the xy plane, and the black holes confine the particle in the z direction. But you may have some sort of a tingling sense right now, because, wait a minute, the electrostatic part can only trap like charges. Because if you try to trap like both charges together, one of them will be repelled, one of them will be attracted, it will be a disaster. However, mass doesn't have charge. So we can trap a neutral plasma in this setup. That's why, even though it seems so unlikely, you may be thinking, oh my god, like black holes and there's a magnetic field aligned with it, this is so far-fetched that it's just useless. But being able to trap a neutral plasma makes it interesting. Let's see what else makes this trap interesting. Once again, emphasizing trapping a neutral plasma. Secondly, this is much more versatile than our pole trap analogy, because the black holes do not need to be equal mass. It is flexible up to mu equals to 0.75, which means one black hole can be 3 times larger than the other one, and we will still have an analogous penning trap that can trap a neutral plasma. Also, black holes can be charged, can't be charged, doesn't matter. It is still stable. And also, the magnetic field that I just said does not have to be completely aligned. It can, in fact, be 10 degrees of axis, so quite flexible. And also, we can trap particles with different mass to charge ratios. Well, that you may be thinking was given, because if we cannot trap protons and electrons, it's not even funny, but we can trap dust, dark matter, heavier ions, everything. This means that this trap actually likely exists somewhere out there in the space. And even better, it may have a possible electromagnetic signature, and we can detect this analog of a penning trap in outer space. From a more phenomenological perspective, the motion of a particle in this kind of a trap is also identical to the motion of a penning trap. Let's see how I'm doing with time. Oh, okay, I'm doing very well with time. Well, I just said something phenomenological. I said the motion of the particle in our analogous gravitational system is similar to a penning trap. But what are the motions in a penning trap look like? Well, a particle in a penning trap has three types of motions. The cyclotron motion, that is small circles due to the Lorentz force. We have an axial motion that is due to the end caps trapped in the z direction. And we have a magnetron motion that is a bigger circle. And all of these frequencies are actually analytically calculable in a penning trap, but unfortunately in our setup they do vary a little bit. That's why I'm going to skip the analytical calculations of the frequencies. Well, let's break down what causes the motions of the penning trap and how our analogous setup can replicate all of these motions. Well, cyclotron motion is created by the magnetic field and the Lorentz force, and we have a magnetic field in our setup. Check, done. Axial motion is created by the end caps, and we have two black holes which can trap both of the particles. That means we can also replicate the axial motion. And the magnetron motion is actually caused by a little bit more complicated setup, is the constant radially outward force from the end caps. And that is also known as the F cross B drift, or if you have heard E cross B drift, F cross B drift is E cross B drift divided by the charge of the particle. So F cross B drift, you can read this, but if a particle is subjected to force F, constant force F, perpendicular to the magnetic field it is subjected to, it actually drifts to the direction F cross B. And in a penning trap, F cross B drift, if we have the end caps here, and if they are creating a radial outward field, we can do a right-hand rule and show that, whoop, we'll have a radial motion starting out of the page. And in our binary black hole system trap, if a particle is closer to one of the black holes, then we will have a net force toward the black hole that is closer, then the magnetic field is out of the page, and F cross B is downward. So does everybody understand the F cross B drift and three types of motions that I have mentioned? Because now I'm going to refer to them constantly, both in sanity checks of the simulation and also while I'm describing the motions of the particle. So how do we actually replicate the motions of a penning trap in our exact trap? This is output of a simulation. You do not have to worry about the exact precise numbers. This is for decent visualization only. And we can see a particle starting at drop down from some sort of a z displacement, in this case just 10 meters, and going through cyclotron motion in the x and y direction, and drifting towards the negative y, as we have seen in the F cross B drift. And this is somewhat of a sanity check. Another sanity check is that when we slightly change the parameters of the simulation, we can replicate the exact magnetron and cyclotron and the axial motion in full cycles and see exact behavior of a penning trap. This shows the motion of the guiding center of the cyclotron motion, full axial motion cycles, and the magnetron motion caused by the F cross B drifts. But what do these two slides have told us? Well, there are different types of particle stable trajectories. That's what they told us. But what makes the particle trajectories so different? Why can we just, in some cases, see the only cyclotron motion and an F cross B drift, while in the other cases we can see all the motions, or sometimes cyclotron motion is not visible? Well, it depends on the ratio of the cyclotron frequency and the orbital frequency. And the orbital frequency is the frequency black holes rotate within each other. So for 250 solar mass black holes, if we make a table of black hole distance, merger time, orbital period, and what kind of a behavior we will expect, and these are all details about the motions of a particle in a gravitational penning trap, between 1/10 of an AU, the black holes will have a merger time of 10 million to 100 million years, and orbital period of 1,000, orbital period to cyclotron period ratio of 1,000 to 10,000. And in this case, we do not see any apparent magnetron behavior. We just see an apparent F cross B drift, more like the first picture you have seen. If they are around the hundredth of an AU, then they have a merger time of 10,000 years, and an orbital to cyclotron ratio is around hundreds, and we see the penning trap-like motion in all directions. And finally, when it is around 1,000th of an AU, the merger time is within 10 to 20 years, and orbital period to cyclotron ratio is 6 to 12. And this is where it starts to get weird, because only 6 magnetron, like cyclotron magnetic motions, are done before the black holes have fully rotated. And this actually creates a pole trap-like stability, and now we are starting to get a small crossover. But I usually prefer to study this in a graph or a figure to understand what's going on. We have the 3 regions of stability that we have outlined, and we have the long-term stability where the black holes will not be joining each other for 1,000,000 years, and this is the time that the trap is going to be filled up. And this is the interesting region around 1/100 of an AU black hole distance. This is where we see all the penning trap-like motion. And then finally, this is the limit that we see the pole trap-like motion. And as the black holes get closer, then actually we cannot characterize the behavior of the particles as a single particle approximation. The black holes end up being too strong, and we do not have as nice of a trap. But again, I'm here to actually collaborate on this project and discuss how we may characterize when black holes get further in. So this project, unfortunately, is not fully complete yet, but we are hoping to complete it in 2 weeks. Well, a quick checkpoint summary of what I had said so far, because I mentioned different kinds of concepts, and it may have gone over people's head, and it may have gone over my head too, so it's a good recap for myself. Well, first of all, these results were under the approximation of non-interacting particles. So all of the simulations and all of the regions of different kind of stability I have shown were done by simulating the behavior of a single particle and assuming all the rest of the particles will behave in a similar way. To visualize this or simulate this or understand this in a more denser, actually particle interacting way, we need expensive plasma simulations. But still, non-interacting limit is not too small. It's 10 to 12 particles per centimeter cube, or around that order of magnitude. So we still can trap quite a lot of particles. So this simulations demonstrated that this gravitomagnetic analogy is stable under a variety of conditions, and it is stable for a long time. Which means, once the particle falls in our trap, it cannot get out. Unfortunately, this brings another question. How do the particles end up in the trap if they cannot get out at all? Well, recall that the space is not really completely empty, and the H2 regions in the galaxies, H2 are ionized hydrogen, if anybody from non-astronomical background is watching this video. And the the calculated electron temperature of our trap for particles to be stable when the black holes are 0.1 AU away is between 10 to the 4 and 10 to the 5 Kelvin. So why did I tell you this random fact? Somebody may already say, wow, this is kind of close to the temperature of the H2 regions that we have. So woohoo! We can trap some things in the H2 regions. But I just set the scene now. How will the process of actual trapping work? Well, the system will go through an H2 region in the galaxy. Each black hole will accrete mass with the BHL mechanism. And if you don't recall how it was, here's a simplified diagram of a single black hole BHL mechanism accruing mass. Masses near the black holes will be consumed within 100 years, but mass that is accreted near the center of the trap will be here forever, even after the system leaves the H2 region. And here is a diagram Mikhail made how actually the BHL accretion works in a binary system that is consisting of 2 black holes instead of a single black hole. First of all, the particles can only enter through a direction that is somewhat perpendicular to the magnetic field, because if they are parallel to the magnetic field, if they are somehow perpendicular, they will just start doing cyclotron motion without our gravitational trap. Also, the magnetic field does not have to be fully aligned, but the particles, the black holes, I have also made this diagram almost yesterday, and I haven't studied well before, and it talks by itself. But yes, simply particles come from here, they get accreted, and near the center, they stay. And we can discuss about this diagram more in the later questions without really digressing from the main part of the talk. So we just simulated or we just drove some way how this trap can trap particles. Unfortunately, there is a caveat to this. The magnetic field does not have to change. It should stay relatively aligned or within 10 degrees of the 9 perpendicular to trap. The warning is that the magnetic field has to keep being aligned perpendicular to the plane of rotation to the binary system while it's passing through the H2 region. But H2 region, it's not empty space and complicated things happen. So it is some sort of a bold assumption that it will stay the same. Hopefully it will stay the same. We will see if it will stay the same in the next 2 weeks. And we will also think that what will be the relative velocity of the particles that are passing, that are being trapped, how fast this trap fills up. These are all further questions that we have. But let's now talk about the possibility of the electromagnetic signature that is associated by this trap. Because I have been emphasizing this very excitedly, and let me tell you how it works. Well, as the black holes get closer, the trap becomes smaller. So we always trap particles within 10% of the black hole orbit radius. And this actually rule of thumb is relevant until 0.004 AU, 20 years before merger. So that actually creates new and unique prospects of electromagnetic emission due to a late release of accreted mass. If I would give an example, I didn't write the specific numbers in these slides because they could be intimidating, but if we have a collisionless limit of 10 to the 12 particles per centimeter cube, then in the last volume of 10 to the 22 meter cube, we can trap 10 to the 14 kilograms of particles. And if 10 to the 14 kilograms of particles are accreted in a black hole in 1 day, then it creates an electromagnetic signature as luminous as the sun. Or if we go to the non-collisionless limit, a limit where particles can collide, then as the trap gets denser and denser and denser and denser, it will introduce some sort of an optical depth to the system, and the system could be luminous even before the black holes merge. So we can actually have a signal of binary black holes merging before they merge, and we can detect it, and then we can try to map some gravitational maps from LIGO to the electromagnetic signature that we have received. But even though this sounds pretty cool, we need plasma simulations that are expensive to have an understanding of this. Well, again, I have mentioned Paul traps, penning traps, some sort of analogies, some sort of electromagnetic signatures. So what do I want you to get out of this presentation is that there are natural analogs to completely artificial Paul and penning traps. So these are binary black hole systems or charged binary black hole systems. So we can actually use Paul traps that are present in labs to study systems that we cannot experimentally study. And this also opens up a whole new research area of searching for artificial analogs within our universe. And additionally, the confinement of particles in the way I described in 3 dimensions, as far as I know, have not been studied before, and purely gravitational systems was not able to do that. So now we introduce a gravitational system that traps the particles in 3 dimensions. And I guess most importantly, the penning trap analog can trap a neutral plasma in this space, and we may possibly be able to observe what we claim exists out there. And here were the resources I have used to finish this presentation, and I thank you all for your attention of this multidisciplinary thing where I sometimes slowly messed up. And please let me know if you have any additional questions, and because I think this deserves a long discussion.
Yeah, thank you very much. So any questions or comments for Ali? Yeah, maybe if you have
Henry?
Yeah, open Henry.
So do you really need black holes, or it would work also with binary of neutron stars?
Unfortunately, we will need black holes because even though black holes seem very complicated, they are much more stable systems than actual stars. The actual stars have gases, they sometimes have solar flasks, they have additional problems, they have different kind of charges throughout static equilibrium.
The magnetic field also.
They may also create their own magnetic field, and black holes are stable and merge for, like, it takes so long for them to merge, and this makes the system easier for black holes. And I do not know whether the stars can have a stable charge. In our statistical mechanics classes, maybe we have, I don't know if you have seen before, but with the equilibrium of particles constantly being repelled and attracted back, the stars per solar mass can have approximately 67 coulomb of charge, which is out of the stability region for physically plausible particles.
Yeah, I didn't mind neutron stars, but okay, they have a strong magnetic field.
Yes, neutron stars, the magnetic fields of the neutron stars itself are quite strong, that I think they will dominate over the background magnetic field. And the reason that we have used black holes and 50 solar mass black holes is that the magnetic field caused by their accretion disks would fall as a dipole, and relatively the center of the trap is far away from the black hole itself, and within these distances the magnetic field of the black holes would be negligible compared to our background magnetic field. Thank you for the question. That was a very nice thing that I've really wanted to address.
It would be applicable for systems like maybe old, in principle, like old white dwarf, because the magnetic field is typically weakening also for neutron stars, so it's higher when they shortly after supernova.
Maybe binary white dwarfs, but the definition of a white dwarf is that, like, don't you need two systems or type 1a supernova? I don't know how you can find a binary white dwarf system in the universe, but
yeah, I think it's probably more complicated in general. Yes,
I think
black hole binary.
Henry had a question.
Yeah. So you mentioned in the Penning-like trap that the magnetic field had to be relatively aligned with the orbit of the black holes. If it traps particles in there and then it moves out of the H2 region to potentially a region where that magnetic field is no longer aligned, how will that cause the trap to behave?
Oh, that's a great question. And this actually, once we get rid of the magnetic field, the system is quite similar to the analogy that I have mentioned, right? Pole traps without the charged black holes. That means as the magnetic field vanishes, I don't know how fast it will vanish, but every particle that was trapped in the system would escape the system as they were put on a hyperbolic potential. Will that create an explosion? It depends on how fast the magnetic field decays. Maybe, hopefully it will, but that was something we were discussing with Mikhail yesterday. And yes, it is an interesting way to think. Whether if we put some particles in a sudden settled potential, how would they all behave? Thank you.
So you only considered protons as the particles, right?
Well, we have considered protons and electrons because electrons behave exactly the same. I can show extra plots offline if you're interested. They behave the exact similar way. The only difference is that their cyclotron frequency, cyclotron radius is much smaller, cyclotron frequency is much higher, and also you can trap electrons for a longer time than black holes than protons because they interact with black holes by mass a little less. Yes.
Yeah, so my question is, did you consider also other particles like some charged ions? Because both of the ball and both of the traps basically they scale with the ratio of charge over mass, right? And if you use different, like the stability conditions scale it. So if you use different particles, then you can have different systems that have stable traps for like different types of particles. So
are you talking about for Paul traps or Penning traps?
Both.
For both. Yes, you can create any arbitrary particle to black hole mass ratio system that would result in the parameters that A and Q. So you can also, I don't know, trap tungsten ions. Actually, trapping them creates a beautiful penning trap motion, but how would tungsten ions come in the outer space? I didn't really know that. You can also trap dark matter, which has like a very different charge to mass ratio. You can trap all different kinds of particles, and the characteristic that it defines, that will define its motion, would be the ratio of its cyclotron to gravitational thing. Sorry, cyclotron motion to orbital period of the black holes. Or in a pole trap, it will be charge to mass ratio compared to the black hole mass. Of course, if you have a higher charge to mass ratio particle, you would need larger mass black holes.
Yeah. So this is now a standard theory already, the dark matter is charged somehow, or?
Well, that was actually a recent paper in, I think, 2022. I think we were talking with Louis about the charge to mass ratio. And
yeah, maybe they asked, yeah.
So I think the mass of the dark matter was like, we said, one electron volt of charge was approximately 10 to the negative 17 kilograms rather than much smaller. Like.
Are some axions or?
I do not recall right now, but axions are much lighter than that, so I do not think so. Axions are, yeah.
But on the other hand, there is also, of course, there are some theories that work with like primordial black holes as some contribution to dark matter. So maybe this is also another. But of course, that's something different because here you are tracking actually.
Exactly. And that said, the black hole, or sorry, the dark matter analogy was only going to be a paragraph in the paper. That's why I did not really mention it here, because then I will have to give a whole new talk. If you guys invite me again, I will be happy to do that.
You mentioned that this works, if I understood it well, that it works until some minimum distance between the, and then there occurs some interaction between gravitational waves and these particles.
Yes, in the single particle systems, until the black holes get close enough to a certain distance, the trap gets smaller and smaller and smaller, and then at some point the tidal force due to black holes becomes so large, the trap actually starts expanding in size slowly again. And that makes the problem less interesting because we wanted dense things that could explode. That said, plasma simulations, if we can make them, will give us a better approximation of a dense plasma perturbed by a black hole. And maybe because of the collisions, the interactions will introduce some sort of an optical depth, and the system can stay stable for 10 more years and then accrete all at once and create an electromagnetic signature. Thank you for that question. Easy?
So, first of all, thank you. I really enjoyed the talk. When you mentioned that we could be able to get a sort of pre-merger signal,
yes.
How accurate do you reckon we can time away how the merger, like how far away the merger is? Like if we get the signal, can we know, there's going to be that merger in exactly 21.25 days?
Okay, so it depends on how fast we accrete matter, which will also depend how fast the black hole would, binary merger would go through the H2 region, and it will also depend that how quickly when we can accrete particles. So let's say we can determine that once we have a luminosity, once we have a density as big as the sun, given that we know the parameters, black holes are this distance. Like I'm thinking of it now, I'm thinking of my answer. There will be too many variables to tell whether this has been how far away the black holes are. But once Mikhail and I finish our approximations, I can give you a better answer. So give me 3 days.
I think this, yeah, so this detection before the merger, this was for this optically thick
optically thick
limit, right? So that this sort of plasma ball would somehow start radiate, right? So it would be like dense enough so that so then basically, in principle, for some systems, but of course then we should estimate like the luminosity of this.
Well, if you want an exact answer based on single particle simulations, I will say exactly 17.8 years, because that is when the system, the trap volume becomes exact density as the density of the sun when the black holes get smaller and smaller. But I don't think that's
So if you have a super non-dense plasma?
If you have a super non-dense plasma, I don't think it will be able to have any optical depth at all. So I don't think it can have, unfortunately, before the merger. We need to accrete that. But that's an interesting thing.
Yeah, but in any case, I mean, what is interesting is that it's qualitatively a new way to reach binary black holes. Could in principle, some of course not all, but maybe small fraction or with some likelihood that they could have some electromagnetic signal like in the last phases of the merger, right? So that's I think like interesting here. So that because previously I think for binary black holes merging, I think there were some papers actually shortly after the first LIGO detection that maybe there could be electromagnetic signal when a collapsing star, like a supernova basically, like somehow when the core is collapsing, it's asymmetric, and then you have maybe in the core of the star you have two black holes, because then you have a lot of material around. So I think there were ideas like this, but I think this is something new for like binary black hole systems.
No, again, Louis warned me, and do not say, please don't ever say something's new, because there will always be some Russian paper before the Soviet Union that hasn't done this before.
Yeah, potentially.
I shouldn't have said that maybe in this country, but are there any other questions? Yes, please.
So thank you for a nice presentation. I'd like to ask, what do you exactly mean by plasma simulation? What do you exactly mean by plasma simulation?
Oh, so...
What type of simulation?
Well, okay. I heard about the myth of plasma simulations, and there are apparently multiple kinds, and I'm slowly getting familiar with these type of simulation. I think Matus knows it better, your PhD student. But any type of simulation that we can see how like a certain temperature gas at certain density behaves with addition of gravitational perturbation. If you have any recommendations of some sort of a plasma simulations that you know exactly fits this description, please let me know. Like, this actually is one of the reasons that I gave this talk. I need help from other people to complete this project. But I don't have a specific answer to that.
Okay.
I think yesterday we were discussing whether, of course, it depends probably on the densities and scale of the system, whether particle and cell approach or some fluid approach is more appropriate. But I think at the moment it's just in the state of evaluation, I would say. I think it's actually to take all the effects into account, it's a separate, maybe, well, you could do it actually for PhD, maybe, like, depends on the duration of PhD, of course. But,
yeah. Any other questions? I had some extra slides of the simulation outputs of Paul and Penning, if you guys want to see like how it exactly looks. But if not, or sanity checks, or versatility of simulations, or different kind of distances output, or some stats, or EM signature details. But yeah.
So thank you very much, Manzi.